The other big idea from Monday was how can we write a set of parametric equations, x of t, y of t, that represent moving in a circle, that represent circular motion. So the piece of paper I gave you to guide you through this shows that the equations come very directly from the definitions of sine and cosine, back when you originally learned them using SOHCAHTOA. So originally you learned that sine of an angle represents the opposite side over the hypotenuse, so that side divided by the hypotenuse, and that cosine of an angle represents the adjacent side over the hypotenuse. Well, okay, let's imagine this triangle now right here in the unit circle. It's called the unit circle because it is radius 1 unit. So it goes through the point 1, 0, and 0, 1, and so on. Okay, so if I think, what is sine of my angle? Here I wrote t as the angle because if we want circular motion, I'm imagining a situation where as time goes up, the time is actually telling me how much my angle is. So when time is 0, I'll have a point there. And as time goes up to 45 degrees, let's say, I'll be at this point. And when time goes up to 90, I'll be at this point. We should actually be working in radians, but right now I just want you to feel comfortable with the idea that as time goes up, my angle is going up, and so I want to describe the xy coordinates of a point that's going around the unit circle. Okay, so let's apply the idea of SOHCAHTOA. Sine of that angle should be the opposite side over the hypotenuse. So this is the opposite side. But notice that that side length is just how far above the x-axis this point is. And so usually that would be called the y-coordinate. Like if I told you this was the point, like 1, 2 or something, the 2 represents how far above the x-axis I am because it's the y-coordinate. The hypotenuse in this case is length 1 because it's a radius of the circle, and the whole circle is radius 1. So if I draw any radius on the circle, it will always be length 1. So by SOHCAHTOA, we've got sine of the angle is the opposite over the hypotenuse, but in this case the opposite side is just the y-coordinate, and the hypotenuse is just 1. So it's silly to divide by 1. So what do I have? I've got sine of my angle t equals y. Okay, if I'm imagining that y is the name of my function, like what's the input number that's affecting y? It has to be this angle t. So I could describe y as a function of t. I plug in a time. That time is the input to sine, and the output tells me my y-coordinate. By the same reasoning, cosine of t is the adjacent side over the hypotenuse. The adjacent side is that side length, which is just the x-coordinate. So we've got x-coordinate divided by 1. Again, I don't divide by 1, and so that gives me that cosine t equals x. But again, t is the value that's affecting the x-coordinate, so I'm imagining x as a function of t. So these are my two parametric equations. X of t is just cosine of t. Y of t is just sine of t. So that's the most basic set of parametric equations to describe circular motion. Come back in the next video because I want you to be able to think very clearly about how changing different parts of these equations will let you make your circular motion bigger or smaller, centered around a different point, make the rotation faster, make the rotation backwards. And you don't have to memorize it. All you have to do is think very clearly about the meaning of different parts in the equation.